All right, in 1.5, we're going to be begin determining limits using algebraic properties of limits. So there are a few theorems, there are a lot, that actually allow us to evaluate limits algebraically rather than what we've been doing, which is estimating them graphically or numerically. So now we're going to get some brass tacks, some algebra. So there's going to be a bunch of these. I think there's like 11. But these are limit laws. They're really important to understand. I know they're probably a little bit annoying to write down at first, but you won't have to explicitly state these very often. But it is important that they're in your notes, okay? And so let's take a look at the premise first. So suppose C is a constant and the limit of f of x as x approaches a and limit of g of x as x approaches a exist. Then the following laws hold. And so the first one just says that the limit of a sum is equal to the sum of the individual limits, right? It's almost like the distributive property, but we can evaluate the limit of f of x as x approaches a and the limit of g of x as x approaches a, and then add those separately together, and that will give us the overall limit of the sum f plus g as x approaches a. And the rest work very similarly, right? So the same goes for subtraction. When you are multiplying by a constant and you're trying to evaluate the limit of a constant times a function as x approaches a, you can just find the limit as x approaches a of the function and then multiply that by the constant at the end. And the same holds for a product of functions. The limit of a product is equal to the product of the individual limits. Same goes for a quotient, with the caveat that the limit of the denominator cannot be 0, because then we'd be dividing by 0, and that is undefined. All right, so we're going to try and use the limit laws I just went over to evaluate the following limits if they exist. And so let's just break down A first. So it says the limit of f of x plus 5g of x as x approaches negative 2. So if I'm going to go in order using the laws, I'm going to say, okay, that's a limit of sums, so that equals a sum of limits. So I can just look at the limit of f of x as x approaches negative 2 plus the limit of 5g of x as x approaches negative 2. But I can take that one step further, right? For the second term in our sum, there's another limit law in play. I have a constant times my function. So there was a limit law that says, oh, okay, well, you can just multiply the constant times the limit of the function. All right, so now let's begin to evaluate these. Let's see what's going on with this graph visually as x approaches negative 2. Well, for f, let's see, negative 2 is right here. For f, which is kind of the red one, that limit does exist. Remember, the limit's concerned with what's going on as we approach negative 2, not what's going on at negative 2. So I would say that limit is 1 plus 5 times for g. That limit exists as well, and it looks like we approach the same thing from the right and the left, and that is negative 1. So 1 plus 5 times negative 1, 1 minus 5 is negative 4 overall. All right, and that's the way we approach it. All right, let's look at part B. The limit of f times g as x approaches 1. Well, we had a limit law. I believe it was law 4 that said, oh, a limit of a product is a product of limits. So you can say this is equal to the limit of f as x approaches 1 times the limit of g as x approaches 1. Okay. So we want to look at 1 here for f as x approaches 1. On the right and the left, the y values seem to approach 2. Great. times, well, for g, as x approaches 1, from the right, we're approaching -1. From the left, we're approaching -2. So that means the limit does not exist. So I have 2 times does not exist, which does not exist. All right, let's work on C, the last one. I'm going to erase some of this on the graph. Now we're looking at the limit of f divided by g as x approaches 2. And we had another limit law that said the quotient of limits is limit. You can take their limits separately and then divide. Oops, what am I doing here? My color coding. But that's with the caveat that the denominator is non-zero. So here, as we approach 2, f does seem to approach the same thing. We're going to have to estimate this one a little bit, but let's say that's like 1.5. But as we can see, g approaches 0. So this limit is undefined, or does not exist. Oh, sorry, I didn't realize my picture was covering the whole thing there. So I split it up into separate limits, but my denominator did approach 0. So the limit does not exist. More limit laws. Like I said, there are a bunch of them. So here we have one for if your function is being raised to a power. You're basically allowed to evaluate the limit of the function and then raise that answer to the power. The limit, number 7, the limit of a constant is a constant. Number 8, the limit of x as x approaches a will just be a. So this is our first peek at what's going to be a very important limit property that we come around to, which is for many functions, you can just evaluate the limit using what's called direct substitution. So you see that again with number 9, which is kind of a combination of limit law number 8 and limit law number 6. And then number 10 is just an extension of that. And number 11 is just an extension of 10. Okay, so if you need to, just pause this, get these written down in your notes, and we're going to move on to the next example. So in this one, I'm going to evaluate the following limits and justify each step. So when they say justify each step, they mean justify it by stating the limit law. Since they're numbered for us, all I'll do is in pink next to it, I'll put the number limit laws that were used in each one of my steps, because we're going to do a few steps at a time. For example, for number 1, the limit of 2x squared minus 3x plus 4 as x approaches 5, the first thing we would want to do is rewrite this as a sum of limits. So all right, and then off to the side, I'm going to tell you what laws we use. So this was from the beginning. That's going to be law 1 and 2. So I'll say 1, 2. All right. So then I'm going to do some, like in that first term, we have a constant multiple times our function. So there was a limit law that said, oh, you can factor out that constant multiple, right? Same thing for the second term. And I'm just going to leave this one alone for now. But the limit law that said I could factor out constant multiples, that was limit law 3. I'm going to say right there, I used limit law 3. And then the last step says these are our newer limit laws from the last page. You can substitute the 5 in here when you have a function that's x to the nth power. You can also substitute the 5 in here, which is our limiting value, when your function is just x. And then this one just says the limit of a constant is that constant. So we used a few of the newer ones. We used 8, 9, and then 7 in that order. What was it? 8, 9, and then 7. Now we're just going to simplify the rest of the way. 5 squared is 25, times 2 is 50, minus 15 plus 4. 35 plus 4 is 39. All right, so let's do one more like that. Go ahead and do part B. Okay, so the first thing I would do is break this up into a numerator and denominator. Right, and let's notate which law that was. That was limit law 5. Right, and then the numerator, I can say limit as x approaches negative 2 of x cubed plus, I'm going to do kind of two steps at once, 2 times the limit as x approaches negative 2 of x squared minus limit as x approaches negative 2, 1. All right, and that's all over the limit as x approaches negative 2 of 5 minus the limit, oh, I'm going to do two steps again, minus 3 times the limit as x approaches negative 2 of x. Okay, so let's verify what our steps were there. So that was splitting it up using, basically using laws 1, 2, and 3, right? Because I was factoring out my constant multiples. So kind of did a mix of all of those. So I'll say 1, 2, and 3 for my limit laws. All right, now we're getting close to evaluating. We're going to use our last few steps, which is we have that law that says if you have x to the n, you're allowed to substitute the limiting value into the function. So that's going to become negative 2 to the third plus 2 times, again, same deal here. You can substitute that limiting value in. So 2 times, negative 2 squared minus, then the last one is a constant, and the limit of a constant is that constant. Same thing in the denominator, the limit of a constant is a constant, so this is 5 minus 3 times, we have that limit law that says if your function is x, you can just substitute the limiting value in right there, so 3 times 2. All right, so we end up with negative 2 to the third is negative 8, plus 2 times negative 2 squared is 8, minus 1, over 5 minus 6, negative 1 over negative 1, which is 1. Oh, I forgot to verify what my last steps were, or my last laws were. I was using basically 7, 8, and 9, right? There we go. So I'm going to say that was 7, 8, 9. So I've evaluated both of these, and I've justified each step with which limit law I used. Okay, last law, the direct substitution property. This is what we were kind of building up to this entire time. And it says, if your function is a polynomial or a rational function, and a is in the domain of f, then you can just do a direct substitution of a for your x, and the limit will be f of a. So that makes these that much easier, which is what we ended up doing. So just to show you, for example, this is a polynomial function. It's a second degree polynomial. And so they say if you're trying to evaluate the limit as x approaches 5, you can just substitute that 5 in for all the x's and simplify, and there's your limit. So my limit is just 2 times 5 squared minus 3 times 5 plus 4, which is, guess what? 39. Same deal here. This one is a rational function, which is a polynomial divided by a polynomial. And it just so happens that -2 is in the domain of that function. And I know that because if I plug in -2, it does not make my denominator 0. So what that says is we can just do a direct substitution of my limiting value in for all x, which is what we actually end up doing when we're using the limit laws. Simplify and get the same exact answer. All right, so with that in mind, here are a couple of student examples. Give those a shot. See if you can come up with an answer, and we'll go over them in class.